Today we're reviewing foundation drawings, reading, understanding, and verifying structural support systems. Now, everything that happens above grade depends on what happens below it. You can correct a finish. You can adjust framing. You can even replace a door. But if the foundation is wrong, the cost of correction multiplies quickly. Structural movement, cracking, drainage failures, and long term performance issues almost always trace back to something that was missing or rushed during foundation work. Foundation prints are not excavation guides, they're precise documents that define how loads are transferred safely into the earth. They establish alignment, depth, reinforcement, and relationships that will never be visible again once concrete is placed. From a leadership standpoint, foundation drawings require discipline. This is not the phase to skim and assume. This is the phase to slow down, verify, and confirm. A strong project mindset begins with respect for with what is buried. Let's begin with footings, foundation walls, and plan views. Footings are the lowest structural elements that distribute building loads into the soil. Their size and depth are not arbitrary. They are determined through engineering calculations that consider building loads, soil bearing capacity, and code requirements. On foundation plans, footings are shown in plan view. You will see outlines that indicate continuous strip footings beneath walls, isolated pad footings beneath columns, or stepped footings where grade changes. Depending on the drawing style, some elements may appear as solid lines, while others are shown as dashed or hidden lines to indicate components below or beyond the immediate cut plane. Foundation plans establish layout. They show the relationship between footings, foundation walls, columns, center lines, and grid lines. These drawings align structural system with the framing and architectural layout above. If alignment's off here, alignment above will reflect that error. Footings often vary in width and thickness. A footing supporting a bearing wall will differ from one supporting a concentrated column load. You may also see special footings for chimneys, heavy equipment pads, or structural frames. These variations are clearly identified through dimensions and notes. It is critical to verify that field layout matches the specified sizes and locations. Foundation walls transfer loads from the superstructure down into the footings. These walls may be poured in place concrete or concrete masonry units, depending on the design. Their thickness, height, and reinforcement are not negotiable details. These are engineered elements. Reinforcing steel in foundation walls is typically identified through notes and sections referenced rather than detailed bar drawings on the plan view. You may see callouts that direct you to a typical wall section where rebar size, spacing, and placement are defined. This requires cross-referencing. It requires research. It requires paying attention. Elevation references are one of the most critical components of foundation prints. You will see notes identifying top of footing elevation, top of wall elevation, and sometimes bottom of footing elevation. These values are measured from a known benchmark. If the benchmark is misunderstood, then it's going to create misunderstanding in everything. Excavation depth, slab thickness, framing heights, door thresholds, these all depend on accurate elevation control. Ignoring a single elevation note can create alignment issues that cascade throughout the structure. Now, let's move to sections, reinforcement in slab systems. We talked about plan views, which are going to show us the layout of the building. Sections show intent. A section drawing provides a vertical cut through the foundation. It reveals the footing depth, the wall thickness, reinforcement placement, slab thickness, vapor barriers, insulation, and soil conditions. Many of the most important foundation components are only fully understood by looking at a section. For example, a plan may show a continuous footing, but the section tells you how deep it sits below grade, how thick it is, and how reinforcement is positioned within it. It clarifies concrete cover requirements, which are critical for durability and code compliance. Reinforcement resists cracking, settlement forces, and load stresses. Foundation prints specify reinforcing bar size, spacing, and placement. You may see notes such as number 5 bar at 12 inches on center, horizontal and vertical. You may see welded wire fabric specified for slabs or sidewalks. These aren't suggestions. Inspectors verify reinforcement before concrete placement. Failure to follow reinforcement notes can result in rejection, delays, and structural concerns. Slab-on-grade systems are common in both residential and commercial projects. Some slabs are non-structural, designed primarily to provide a finished floor surface. However, others are structural and they're designed to support loads and resist movement. Foundation drawings indicate slab thickness, reinforcement requirements, and relationships to foundation walls. Some slabs are poured independently after the walls are constructed. Others are monolithic pours where footings and slab edges are integrated. You will also see thickened slab edges or turned down footings where additional support is going to be required. These conditions must be carefully reviewed to ensure formwork and excavation reflect the intended design. Expansion joints are typically shown where slab meets walls or columns. These joints allow for movement due to things like temperature change that could cause shrinkage or expansion in the slab. Without proper joint placement, slabs can crack unpredictably. So foundation prints identify joint locations and sometimes joint types. This can also mean green cutting with a saw. This allows for a relief area for any cracks to follow. Insulation must follow these specifications precisely. Waterproofing and vapor barriers are also addressed in sections. Vapor barriers beneath slabs prevent moisture migration into the building or into the flooring that is going to be put on top of the concrete. Waterproofing on exterior foundation walls protects against groundwater intrusion. These systems are often shown through symbols and notes rather than detailed drawings, which means they can be easily overlooked. Durability depends on these layers. Moisture intrusion is expensive to correct once the building is complete. This is often where we come up with our mold issues. Now, let's address specialized foundation systems and elevation coordination. Not every project can rely on conventional spread footings. When soil conditions are unstable, which you would have learned in your soil report, we're going to find out whether it is weak bearing capacity, expansive soils, or high groundwater. Engineers will design deep foundation systems to match any of those circumstances. Auger cast piles are one example. These are drilled shafts filled with concrete as the auger is withdrawn. They transfer loads deeper into stable soil layers. Multiple piles are often grouped and connected with a pile cap to support columns or walls. Caissons operate similarly, but are typically larger in diameter and they may extend into rock. Steel piles are driven into the ground until sufficient resistance is achieved through friction or end bearing. Foundation prints show pile locations, spacing, and connection details. These systems require careful coordination between geotech reports, structural drawings, and field operations. Misinterpreting pile elevations or cap dimensions can create significant structural conflicts. Elevation coordination becomes even more critical in these types of deep foundation systems. You will see notes identifying top of pile cap, bottom of footing, slab elevation relative to finished floor. These values must align precisely with framing heights and architectural thresholds. From a project leadership perspective, foundation elevations should be reviewed early and verified in pre-construction meetings. Field crews, supervisors, inspectors, surveyors, and engineers must share a clear understanding of reference points. This is where mindset matters, not in theory, but in practice. A leader who insists on verification prevents downstream corrections. Foundation prints define how a building is supported, stabilized, and protected from the ground up. They establish load paths from structure to soil. They clarify reinforcement requirements. They define slab relationships. They respond to soil conditions. Reading foundation prints requires slowing down. It requires cross-referencing plan views with sections. It requires verifying elevations against benchmarks. It requires confirming reinforcement before placement. When foundation drawings are interpreted correctly, confidence increases across the entire team. Inspectors trust the work. Engineers see compliance. Project managers protect schedule and budget. Everything above grade rests on decisions made during this phase. As construction professionals, our responsibility is not simply to build it quickly, it is to build it correctly. Foundation prints demand that standard. When you approach these drawings with discipline, verification, and clarity, you reduce risk before it ever happens. And that is where strong project leadership begins, at the base, where no one else will see it, but everyone depends on it.